only reason I replaced this computer. Okay. So, this right here is when we're talking about the periodic table of elements. And one of the big skills that you'll be able to use in this class to really benefit yourselves and have a much easier time on exams and in general understanding chemistry is being able to understand and read the periodic table. So the periodic table is the way it is because of the chemistry and the world around it, okay? Like if you were to change the number of dimensions, there's 3 dimensions in space, right? You can go forwards, backwards, it's 1 dimension, side to side, up and down, right? Okay, those are the 3 dimensions of space. If you were to change that, it would actually change the periodic table shape. You'd actually have to rearrange the periodic table. And so that periodic table is actually telling you a huge amount of information about the universe by almost every factor of the periodic table. The shape, the reason it has those 2 columns on the ends like that. The reason it has certain numbers, why it has fractions for the masses. Everything about the periodic table tells you something, okay? It's very intentional in its design. And so, for example, the groups here, things are actually grouped for another reason, but they're ending up being grouped because of their chemical properties, okay? Remember, the groups are actually those columns, right? So they exhibit very similar chemical properties. Typically, the IUPAC, which is the Union of Pure and Applied Chemistry, they're the people that come up with the periodic table and designate new names, etc. A little kind of funny thing about IUPAC, by the way, is that IUPAC used to be really, really contentious with each other. There were about 3 personalities that really hated each other in IUPAC, and for 10 years, they actually got into an argument and then didn't meet and assign any new names for about 10 years. So they had like a really big blow up at one of their meetings. And they're like, screw you, and then didn't name anything new. And so have you ever seen the periodic tables, especially probably from your childhood? They have these sort of outlined names on the bottoms. And a lot of them have like 3-letter designations. Those were unnamed compounds. They were just given a code because nobody named them yet. And it was like that for about 10 years because of personalities. So in case you're ever wondering, can scientists be childish and have personality issues? Oh, yes. Oh, yes. Being a world-class scientist has nothing to do with personality or wisdom. Now, my advisor personally knew most of those people, and he used to purposefully not use some of the new stuff they came up with and said you should do. And anytime somebody would call him on it, he'd be like, I was here before those fuckers. Tell them to go screw themselves. So he was a real character. Anyways, they have actually designated a system that's number 1 through 18 for the columns. These are called the group numbers. You will see on a number of periodic tables that they do not just do the 1 through 18, or they don't do that. Because I guess they also said, just like my advisor. But a lot of people end up using the AB. So that's group 1A, 2A, 3A, 4A, 5A, and you see how we've skipped the 10 in the middle? So that's what's happening if you ever see that. Okay? A lot of you probably only ever heard these, group 1A, 2A, 3A, 4A, etc., and never even realized there was an 18 here. Because a lot of people ignore those. Okay? Especially like high school, middle school level chemistry, they'll almost concentrate completely on this stuff right here. And won't talk about this stuff down here at all. And we're mostly going to end up concentrating on these rows here, which are called the periods. Okay? Periods 1 through 3. Can anybody tell me why we would mostly end up concentrating on these periods? So if we were to go by weight of the solar system, like percent of the solar system, how much of the solar system do you think is accounted for when we get to here, helium? It's about 90%. And then once we get down here, it's the vast, vast majority. There's almost nothing else. Okay? These are actually very small amounts of the solar system. Interestingly enough, lithium and beryllium here are actually, you've heard of lithium, right? Lithium-ion battery. Yeah. Lithium is actually something that's extremely rare throughout the universe. It's one of the more rare elements. And there's reasons for that. We won't be able to get into them this semester because they're just, but it has to do with how a star forms the elements. Okay. All right, so the periods, these are the ones that are the horizontal rows going down. They're numbered from 1 through 7. 6 and 7 are set apart from the periodic table. That's that insert that I was talking about before. You will probably never really encounter this stuff down here. Though if you're going into a medical career, you'll encounter it tangentially because that's what the radiation ward portions will have. Okay, they'll have elements that are down here. Okay, there is the metals and the non-metals. So when you saw the staircase-looking thing here, can everybody see the staircase? Okay, the zigzag line. All right, that staircase right there is what separates the metals, which are over here, from the non-metals over here. And see the coloring for these different atoms? How we have blue and yellow? The yellow is the non-metals. The blue here is the metals. Everybody see there's greens right here? They're the ones that are touching that staircase, except for aluminum. Okay, so the green things here that are touching that staircase are typically called metalloids. Full disclosure, your book actually may be a little wrong in which ones are metalloids and which ones are not metalloids. It's something that changes every few years because there's new tests that get thought up to divide, is that a metalloid or a metal or what? Okay. Really, honestly speaking, just everything that's touching the staircase is kind of metal-like, okay? And also has some not-so-metal properties. Even aluminum has some not-so-metal properties, okay? It's just where exactly you set the line, right? Where is the line between salmon and pink? Does it really matter that much? Probably not, right? Yeah. You just got to know that it's not perfectly a metal in these cases, right? It's not perfectly a non-metal in these cases. All right. So several elements are going to be essential for human health. This class is going to have a pretty strong focus on human health and in general, like a sort of science of health, science of medical, okay? Sort of intro to it. We'll take the opportunity while we're learning that to learn chemistry as well. Who here's nursing, by the way? That's a pretty good, strong showing, right? Are you all already accepted in the nursing? No lab? No? You ended up needing to do the lab. Yeah, so if you're already in the nursing program or already have went through the stuff, you cannot take the lab. Otherwise, they always want you to do lab. And for certain reasons, the lab is actually preferable for like scholarship stuff and grants and stuff. So I'll be seeing most of you in lab then. Be fun. Okay, so those are needed in the largest quantity in human health are, of course, carbon, hydrogen, oxygen, nitrogen. These are what make up the vast, vast majority of biological molecules. These are what make up things like your proteins. These are what make up the things like the fats. These are what make up the things like the carbs. Okay, your cells mostly made up of these elements. Macronutrients is going to be what you need in quantities that are greater than 100 milligram per day. There's stuff that you need to get in your diet almost all the time in quantities that are enough that you're not just going to accidentally get them. Okay? And so these are going to include things like sodium, magnesium, potassium, calcium, and chlorine. By the way, nowadays in the United States, we consider sodium what? You always hear about sodium levels as being bad, right? Okay. Do you know what the leading cause of holding back human population was for every other decade in human history other than the last 100 years? Sodium. Nobody could get enough sodium. Yeah. So it actually crippled populations. It actually caused population declines. It actually caused the Europeans in the Northern Europe to not be able to expand out. This is why most of the population centers were on the sea, by the way. Partially the salt trade. Okay. It's kind of an interesting thing that we think of it as a bad thing now, but go back 100 years ago, you have been like crying, I need salt. Micronutrients is going to be needed in quantities less than 100 milligrams per day. They're going to include things like iodine, fluorine, iron, zinc, and quite a few other elements, actually. You'd be surprised in some of the things that end up in here. For example, did you know you need copper? Yep. You need copper. I know, right? Did you realize that you need copper in your diet? Go lick some wires. Yeah, you get a little bit of copper in water, as long as it's not too purified. Highly purified water won't have it. Mostly we end up getting it from people that eat meat, get it from mostly the other animals. You can get it from a few other sources. It can be put into some different types of vegetables that have extremely porous bringing up the water. So micronutrients, by the way, are one of the things that there's a real question whether we've depleted some of the micronutrients from the soil in the United States. So like that's a open scientific inquiry people are making right now. So I don't know which way it is right now. Yeah, you need iodine too. That's why it's iodized salt. You ever seen that before? Okay, so these right here are some of the more common elements. Again, those are the common elements in living beings. Right here we have the macronutrients highlighted, and there's the micronutrients highlighted. That's most of the most important ones, though it's not a complete list. How they get these macronutrients is actually they have done some experiments where they've essentially reduced a human or reduced an animal to ash and then gotten what's in it. That does not necessarily mean everybody has the exact same stuff in the exact same amounts. Okay? And so it's actually very complicated what levels of micronutrients you need. All right, so pure substance containing two or more chemically combined compounds. This elements is going to be a compound. Compounds combine elements in specific ratios. So do you know why the chemist went to jail? It's going to be a joke. It's not going to be super funny. But, huh? Oh, that's a good one. That probably happened after this event. So he went into the other room. He shouted back to his friends, "Hey guys, do you want some H2 too?" And they said, yeah. And so he gave them a little beaker full and they drank it. Do you know why that joke is funny? No? Oh my goodness. So, yeah, so he went into the other room. He shouted back, "Hey guys, do you want some H2O2? And so all of his friends went, "Yeah, I want some." And then they tried to drink it. So H2O is what? Water. They thought they were getting water, right? H2O2 is hydrogen peroxide. No. It actually is kind of amusing. Now, When we talk about chemical formulas, this is applying this concept that a compound is its specific ratio of those elements. Okay? So when you breathe out CO2, that is carbon dioxide. Okay? That is one carbon, two oxygens combined together. All right? If a plant puts off CO2, which it does, plants put off CO2 as well. They don't just eat it. Then is that carbon dioxide different than the stuff you're putting out? No. No, it's always the same. If it's carbon dioxide, period. Okay? How about the carbon dioxide that was put out by an internal combustion engine? Is that somehow magically different? No, not really. It has the same chemical properties. It's going to do the exact same stuff in the environment. Okay? And so, you ever heard of Greenpeace? No? It's one of the largest green organizations in the world. It's a tens of billions of dollars funded organization. For 20 years, they had on their front of their website that the CO2 that was put off by humans, by animals, by trees, by cars were all different. And the CO2 that was put off by animals was somehow good and healthy. And the CO2 that was put off by cars was somehow poisonous and bad. Okay? They said this right on their thing. I've had students look this up and then quote this, and it's just total bullshit, right? Absolute crap. No basis in reality whatsoever. Okay? All CO2 is the same. It doesn't matter where it comes from, right? By the fact that CO2 is carbon dioxide, period. Okay? All right, so the chemical formulas, these show things like water, H2O, is composed of two particles of hydrogen, two elements of hydrogen, and one particle, one atom of oxygen. If we look at table salts, NaCl is table salt. It has how many sodiums? 1. How many chlorides? 1. Very good. If I somehow get H2O2, is that water anymore? No. What if I were to do something like H4O2? Is that somehow still water? No. So this is one of those places that students, when they're first learning it, really get tripped up on. Okay? If you have two H2Os, that is not H4O2. Those are very, very different things. Just like having two people is not one person twice the height with 4 arms, 4 legs, and 4 eyes, right? That's a very different thing than two people, isn't it? Okay? And so remember that these are actual designations of what that compound is, right? If you have multiple of them, you put a number out front. Okay? You don't go multiplying the numbers inside, right? It's something that people get tripped up, and there'll be a fraction of people that will get tripped up on that, and then they'll get stuck. And it causes them havoc for a while. Okay. Now again, the chemical formula is going to identify which elements and how many atoms of each element are present in a compound. Let's talk about changes. So when I boil water, do I blow things up usually? No. But if I start like hydrolyzing water to make hydrogen gas, I can blow things up, can't I? Okay? And so there's a very different types of changes that happen in the world, isn't there? There's 2 major categories of changes that we're going to concern ourselves with. There's the physical changes. These are going to be change in the state of matter, representing a physical change. The form of the matter will be changed, but its identity remains the same. One of the ways you can think of this is that chemical compound, the H2O formula, is going to remain the same. Okay? So for example, I can freeze water, I can melt water, I can boil water. These are all physical changes, aren't they? Because I still have water. Okay? I can divide the water up among 2 cups. I can pour it into 1 cup. Still physical changes, right? Because I still have water. Okay? Okay, let's talk about chemical changes now. So a chemical change is going to result in a change in the chemical identity of that substance. If I perform a chemical change on my water, you probably shouldn't drink it anymore, should you? Because it will no longer be water. So when a substance undergoes such a change, it's going to be referred to as a chemical reaction. This is where we start bringing in things like reactions. By the way, right here, this is a chemical change. That is burning coal. Burning stuff is a reaction and a type of chemical change. How about cooking things? That is a what? Chemical change. You got it. How about cutting the thing up to serve it? Physical change. Perfect. Perfect. There is a kind of amusing experiment that's been done. You can look up videos if you want. Did you know you can actually slap things to cook? So if you slap stuff enough times, it will actually cause a cooking reaction. Yeah. So you can do physical changes that result in very, very, very small chemical changes within the system. You got to slap it about 10,000 times, by the way. So don't go try doing this at home. But it's a very, very funny video if you ever look it up. Yeah. It actually does work. How matter changes the chemical equations. So a chemical equation is going to show what happens to a substance involved in a chemical reaction. It's basically our way of putting an equation to tell us what happens in a chemical reaction or chemical change. So here we have carbon and oxygen. They're going to be our reactants. Reactants are always drawn on the left side. Can everybody see our reactants okay? This is what it would look like when you actually write it down on paper. This is so you can better envision it in your head. This is one carbon atom reacting with two oxygen atoms. Can everybody see okay? Okay. And so we get carbon solid. Anybody know what carbon solid would be? What was that previous picture I just showed you? Coal. Yeah, that's coal. Okay. And so it's in the presence of oxygen, which is in the air, right? We provided a little bit of heat to get the reaction started, and guess what happens? It starts burning, doesn't it? And so this reaction, carbon plus oxygen, alongside a bit of heat to get it going, is going to give us CO2. Now, honestly speaking, most coal is not pure carbon, and so this is why you would not want to sit there over coal and let that just go in your face, okay? But if it was pure carbon, and you can get coal that's basically pure carbon, it's kind of expensive, this is just going to provide CO2. Okay. And so this right here is a reaction arrow. This arrow tells us that we go to that other thing, that these combined equal this. When we look at this, notice the name of it. It's a chemical equation. See that equation part of that? Okay. Whenever you have done equations in the math classes before, what are the rules that apply to them? Yeah, you typically read it left to right. How about if you do something to one side of it? Has to be done to the other, exactly. All those rules that apply to math equations, still true, okay? This is a math equation. You can think of this as A plus B gives us C. Or you could think of this as X plus Y gives us some value, okay? This is just a math equation. We've just had very, very, very special variables, don't we? Okay? And those special variables happen to correspond to real stuff in the universe, which is the compounds, right? Actual samples. A lot of coal you're burning. Okay? That's all this is. It always was and always will be just math equations, special variables that represent the real world. Okay? I know it's applied math. gasp, terror. All right. And it's actual math that's happening all around you right now. Okay? Okay, so again, S here stands for solid. L would be liquid. If we have a gas, that's G. If we have something dissolved in water, it's going to be called aqueous. Aqueous is AQ. So you have these parentheses. This tells you what phase it's in. Notice, for example, CO2 here, the product is a gas, right? Okay, very good. Let's go ahead and talk about balancing chemical equations. Well, if we have one C over here, how many C's do we have to produce? The same number, right? 1. And you can't just create mass and you can't create things out of nothing. Okay? If you start the day with 1 pencil, how many pencils should you end the day with? 1, exactly. Is the pencil somehow going to multiply? No. Interesting little factoid. All of your thought processes, do you have a question? Yes. Yep. It means that whatever it is has been dissolved in water. Nope, not any other liquid. Yep. Yeah. If it's dissolved in some other liquid, that would be a solution. And typically you would put SOLN, period, which would be the abbreviation for solution. Aqueous, aqua, which is the root word, water. Yeah. Yeah. Now, it does get misused sometimes, just like every other language, right? By the way, there's 2 things that I'll point out quite often, and this is kind of a weird thing for a chemistry professor to do, is number 1, when I give rules, I'm always going to mention that rules are very rarely something that can't be violated at all. Okay? There's a lot of rules that are just helpful guidelines and are just incredibly rare to see any violations of, especially in this class, because we don't want to go into the 20 edge cases. Okay? And then the other thing that I have a little bit of an issue here with is that a lot of the language that I'm going to teach you, there is the correct way to use it, and then there is the real world. And as we all know, language doesn't always get used correctly, does it? Yeah. And so do realize that, yeah, things are not always used properly. Okay, so when we balance chemical equations, keep in mind that, again, these are things from the real world. If you were to go back 400 years and ask somebody, if you open the closet, will a hydra appear from that closet? They would go, probably not, but is it possible? Maybe. Okay? Why is that? Because back then there was no, you have to have a, like it has to exist and somehow get there. Things could pop into the universe according to people. That was the prevailing thought. So like bacteria just popped in the universe. It just happened. Spirits. Okay? And now you all have a causative effect in terms of your mental, what you think of the mental model of the world. Okay? And so you think there's a cause and effect to everything, right? And so if you're going to find a bag of gold, somebody dropped that bag of gold somewhere, right? It didn't just magically pop into existence. Okay? Now, this thinking actually comes from this right here, which is the law of conservation of mass. That's just managed to percolate throughout the entirety of the world societies that are communicating regularly. And so the law of conservation of mass is going to state that if we have mass, our mass can't change. It has to be conserved. Okay? So if you have something to start, the amount that's at the end is still the same amount, right? Now, having said that, you can lose things by having them escape your flask, right? Or spilling them, okay? But they haven't went down. Your total mass hasn't changed. It just happens to have rolled out on your desk, right? Okay? Same as the money. The amount of money didn't change. You just might have spent something here. You might have dropped it out of your pocket there, right? Okay. So keep that in mind. A lot of the problems that you have whenever you come up with an answer, you can very easily tell, am I right or wrong, right away. And that's because if you have 2 carbons to start with, how many carbons do you have to end with? 2. 1, right? You can't create nor destroy matter, and so you always have to have the exact same numbers on both sides of any of these reactions. Okay. Now, we balance these chemical equations using what's called coefficients. It's how we go ahead and say that we have more than one of these compounds. Okay? So, for example, if you have 2 O2s, you would put a 2 in front of the O2. That'd be a coefficient. Notice the language here is the exact same as math was, wasn't it? 2x, 2 is the coefficient, right? 2O2, 2 is the coefficient. Because O2 is a variable, isn't it? Yeah. It just happens to be representing the real world. Okay. So this is the procedure for balancing a chemical equation. I'm going to give it to you, though honestly speaking, you're going to practice this and then you're never going to look at or think about the actual procedure again. It's just going to become something very ingrained. Okay? It's not actually difficult. Step 1 is to examine the original equation. Is it balanced? If not, you proceed to step 2. By the way, a little statement about difficulty in chemistry. I'm going to say this. You're not going to believe me, but it's okay. Chemistry is far less difficult than you think it is. Okay? Chemistry is something you've practiced every day of your life, every breath you take. Right? Every single moment of your life, you are practicing chemistry. So you know a lot of this stuff. You just have never thought about it formally. Okay? Now, having said that, because this has the name chemistry and there's a reputation to chemistry, you are going to start a problem in a near panic state of, I can't possibly do this. Okay? And so you just need to sometimes step back from it, go, I got this. Right? And then retry. There's a lot of this stuff that you already know, you just have not actually explored it. Okay, so step 2 is going to be balancing the equation one element at a time by adding coefficients to them. You're going to balance the elements that appear once on a side first, because those are the ones that are extremely easy. Step 3, check to see if the equation is balanced. The coefficient should represent the smallest possible set of numbers. If you see that all your coefficients could be divided by a single number and end up being whole numbers, go and divide them. Okay? For example, if I ended up with something like 633 for my coefficients, what should I do to those? Yeah, I should divide them all by 3, right? I just accidentally put a too large number in. Okay? Happens. Sometimes it's easier to do that. Okay? Math. So the math counts. For measurements, we easily compared. You need a defined measurement system. This system is actually called the Système International des Units. It's usually referred to as the SI system. Anybody notice it's in French? Yes, it's in French. Another group that's very contentious and kind of annoying sometimes, does some kind of weird stuff every now and then, but less so than the other groups. This is kind of an interesting case. This was formed because there were 2 universities in France that were the cutting edge of science at the time, and they were using completely different systems for everything they did. So they would talk to each other and get into arguments. This constant is this number in this units. And then the other person would be like, no, that's not right. And they were arguing because they were different units. It'd be like saying it's 3 feet, no, it's 1 meter. They'd actually get into fist fights over this at the local bars. These universities were literally across the river from each other. You could throw notes over to the other university. And they couldn't agree on anything, ever, because they were never using the same units. Every time they said a number for something and tried to talk about it, Didn't make any sense. Okay? And so the System International SI units are the kilogram. That is abbreviated kg. You guys have probably heard kilogram before, kilo, right? Oh, come on. You've all seen movies at the very least. We're shipping 10 kilos of Coke, that sort of thing, if nothing else, right? Hopefully most of you have seen kilogram in some other capacity than drug deals on movies. But the standard units for volume is liter. Liters of petrol is probably, or liter of water is probably the ones you've heard of before. The standard length is meter. Is everybody okay with meter? I think that one gets thrown around quite a bit. You may even know kilometer better, which is 1,000 meters. Okay. We'll talk about prefixes a bit. I've hinted at it just now. Kilo being a prefix. It's a way of representing these so you don't have to write out large numbers. Okay. You will notice this one actually has a prefix baked into the SI unit itself, the kilogram. Interesting note about the kilogram. It was for a very long time an actual physical object. And if somebody had went and accidentally bumped it and scratched it, the kilogram weight would have changed. Like this actual, what it represents would have changed. They kept 5 of them to try to avoid that without somebody noticing. But if somebody had accidentally scratched all of them, we wouldn't know what the kilogram was anymore. We'd have to reset the measurement. That is no longer true. They spent $10 million to make an orb of silicon so they could set it's something we could reproduce from the universe itself. Okay? Instead of having a chunk of metal sitting in a vault somewhere that could get messed up, right? So prefixes in the metric units are going to change the meaning of the unit by powers of 10. And so they're a way of representing very small and very large numbers very quickly by tacking on these prefixes. You may have already kind of seen hints of this and went, oh, what about milliliter? Did anybody, when they see liter, go, what about milliliter? Did you notice the same root? Just has different prefix, doesn't it? Yeah. And so these right here are some of the more important prefixes. This right here is giga. Anybody ever heard of gigahertz? No? Gigabyte? Yeah? Gigabyte, like internet speeds, like you have so many gigabytes left on your drive? Okay. Okay, actually the internet speed is a gigabit, by the way. And that's just to make it look like it's larger numbers, in case you're wondering. So giga actually means 1 billion of the base unit. So for example, in a gigabyte, there is 1 billion bytes. Okay? A gigabit is 1 billion bits, isn't it? All right. Difference between a byte and a bit, by the way, is there's 8 bits in a byte. So when you look at the internet speeds, divide them by 8 if you want to know how fast your download's going. Mega, probably you've heard of megabytes before. Most of your documents are probably in that. Videos tend to be in that. That is going to be 1 million bytes. Notice, if we were to do these to each other, a gigabyte has 1,000 megabytes, doesn't it? See that? We can go from one to the other. The difference being 3 zeros, 1,000. This is kilo, like a kilometer, like a kilogram. There are 1,000 meters in a kilometer. Okay. Anybody notice you asked for being paid $100K? How much would you get paid? 100,000, yeah. K meaning what? 1,000. Why does K mean 1,000? It's kilo. Yeah. You're actually asking for 100 kilo dollars. You've been using prefixes this entire time. You just never knew it. Okay? So that's kilo dollars. You could ask for a mega dollar. Hey, I want a salary of 1 mega dollar. Try that your next negotiation for pay. You only have to pay me 1 mega dollar. If If you really get aggressive, you could go for a gigadollar, I guess. Ooh. Maybe go for a petadollar. That'd be more money on the planet. Pay me everything that will ever exist for money for the next 100 years. Okay. This is the base unit. You don't put any prefixes. It can be any type of unit. There are actually a fair number of units. And some of the newer sciences, or ones that they don't really want people to understand what the hell they're putting out, have not settled on any sort of base units that are usable everywhere. For example, climate science is notoriously bad about this right now because there's a lot of interest on both sides of that debate that don't really want people to be able to read their figures and actually compare them to each other. And so they're very, very bad about this. They'll use 4 or 5 different units for the same thing in the same publication. It's nuts. There are other fields, though, that are extremely bad about this. And it's mostly because nobody's sat down and hashed it out. Okay? Deci. This is decimal. Anybody ever heard of a decimal before? Okay. How many decimals are there in a single unit? 10. Yeah. So there are 10 decimeters in a meter, right? Okay. You can remember this word fairly easy because the root word here is like deca, right? Like decade, meaning tens, right? Okay. Centi, like centimeter. Anybody heard of a centimeter before? How many centimeters are there in a meter? 100. Same root word as century, by the way. Cent. Okay, or cent as in money, right? A penny is a cent. There's 100 of them in a dollar. Milli. Milliliter. Everybody's heard of milliliter before? Okay. Milliliter, meaning there are 1,000 milliliters in 1 liter. Okay. So half a liter would be 500 milliliters, right? Okay. Now, micro. Now, this is called mu. See that U-looking thing that's backwards? Everybody say okay? Okay. So that's actually the symbol that should be used. Mu. It's a Greek symbol. It is a pain in the butt to type Greek symbols. So can you guys guess what everybody uses all the time for this symbol instead? If they're just typing it? They use U. So if you see a U in front of something, it's probably a mu and it's probably micro, okay? And if any of the nurses, future nurses, ever see a doctor's note and it has some loopy thing that kind of looks like a U, but might be an M cursive, ask, okay? Be very careful. These prefixes are one of the more important things I can actually teach you in terms of medical. And I've actually had 3 or 4 nurses come to me after this class, after they've been out in the field for a while, and go, yeah, the doctor wrote something that looked like an M. The nurse that had been there for 10 years was going to give the patient this drug dose, morphine in one case. And I went, no, that could be a micro. I think that's a micro. And she was ready to pump it up, and they went back to the doctor, found out it was micro instead of a milli. So they would have given a drug dosage 1,000 times the drug dosage of morphine than should have been given, which would have killed the person. And that's actually something that happens fairly regularly. Like, it's not all the time, but like it's a 1 in 1,000, which is actually a lot of people if you think about there's millions of people that come into the hospital all the time. So it's one of the reasons everybody needs to know the science to some degree. So everybody can double check each other, right? And go, whoa, not milli, micro. Okay? The other way to represent micro is putting MC in front of something, okay? So like MC and then M would be micrometers, right? MCL would be microliters, right? Okay. Okay, so this right here is nano. Anybody ever heard of nano before? Like nanoparticles? Has anybody heard of a microprocessor? No? No? Aw, that's just sad. Okay, you've probably heard of things like nanocoding, nanoparticles, something like that, right? So nano is going to be 1 billion nanometers are in a meter. By the way, nanometers are actually what the sort of sizes you'd see for like a computer circuit. Okay? Those are the sort of thicknesses that you'd see there. And that's why if you ever look at the computer chips in your devices, they say things like 5, 7 nanometer. That's the technology level that they're at. Micro, by the way, anybody ever heard of microbiology? Guess what units in terms of meters you use? Micrometers. They're measured in micrometers. Okay? And that's why microbiology is called microbiology, right? Because it's micrometer level biology. Okay? Okay, anybody have any questions about any of these? Right. Please get these prefixes down, get comfortable with these prefixes or something that you want to just have down, because this is the sort of language we need to be able to use to discuss anything scientific, right? Without the language, we just can't understand any of this. Okay. So let's go ahead and talk about some equivalent units. For example, if I have 1 deciliter, that means I have 0.1 liter, don't I? They're the exact same thing. There's no difference between those. Okay? I could freely express it either way. Why would I choose to express it one way versus the other? Because people don't like writing out fractions. That's it. Okay? I can do conversion factors or equivalency. So this is an equivalency. They're equal to each other. This is what's referred to as a conversion factor. It's where you have put one over the other. Because they're equivalent to each other, I'm actually just saying they just equal 1, don't they? They would actually cancel out. Okay? And so I can always do a conversion factor in any sort of math problem at all. Because I can always multiply anything by 1 on both sides, can't I? Okay? So conversion factors can go in anywhere all the time because they're just multiplying by 1. They would cancel out. Okay? Okay. Now, having said that, conversion factors actually have to be equivalent. Okay? So, could I do something like 10 deciliters over a meter? No, that's not a conversion factor. That's not an equivalency. They're just not the same things at all, are they? Okay? These things have to actually be equal to each other. Okay? So I need to be careful about that. People get into the math, they start doing things like that. Okay? And they start getting confused. All right, so let's go ahead and talk about converting units. A lot of people like to call this dimensional analysis to sound fancy. Okay? If you ever heard dimensional analysis, that's what it means. It just means converting units. Step 1 is going to be determining the units that you want for your final answer. That needs to go in the top somewhere. So, because that's what you want to get to, right? Step 2 is establish the given information. Every problem, no matter how complex, can actually be moved towards solving it. This is not just for math, this is for life in general, by stating what do I have, what do I need, and how do I get there. Okay? No matter what the problem is, whether it's some major philosophical problem in your life or a math problem in chemistry. Okay? What do I have? What do I need? How do I get there? Right? You can always move towards solving it. All right, so we're going to decide how to set up the problem, which conversion factor should be used to leave the desired unit in the answer. So, now there are many different ways to get to the final path in math because it's a language for the world, right? There's many paths to a given destination. This is probably the easiest for most people to understand, where you take the given unit, the one you've been given, You've been given some value. And then you go ahead and multiply it by a conversion factor that moves you towards the desired unit on top. Okay? And then what you want to do is have the unit that you want to get rid of on the bottom. That's the overall gist of these things. Okay? Now, I personally find it easier to start with the desired unit. So I oftentimes use the conversion factor with the desired unit and then cancel things off of that. I'm a nonlinear thinker though, so there's like maybe 2 or 3 of you that would be like, yeah, that seems easier. And everybody else looks at me like, what in the world, Dr. Clausen? That's just not okay. Okay. So you can do that, by the way. You remember that they're transitive. You can go ahead and start with any part of a multiplication problem. Okay? You can reorder freely multiplications. All right. And divisions for that matter. Step 4, solve the problem. So we're going to go ahead and solve the problem. Now, one of the things I want you to have in the back of your head is a sort of Dr. Clausen voice or some voice in the back of your head that goes, hey, express your units. Write your units out. Cancel your units. Okay? All the problems can always be done with 100% accuracy in this course with no real effort by just canceling units. Right? 90% of the problems people are going to have doing these problems is because they're going to get lazy, not write out their units, and then they never are sure if they've canceled their units and they don't know what the answer should be. I'm not sure if I'm right or not. If you state your units and cancel your units out, you always know if you're right or wrong, and all you ever have to do is swap around units to get them to cancel. Okay. Once you sort of realize that you just are canceling units, that's all you're doing for these problems, they become incredibly easy. Okay? All right, so significant figures. This is going to be a measuring matter. We're going to have a limit of the precision we can achieve, and so this is going to rely heavily on the precision of the instruments that we can use to measure it. All right, let me make that a little bit simpler for you real quick. Okay, so I'm trying to bake cookies, okay? Okay, when I bake cookies, what do I need to bake them? Can I just take a container of salt and that's about a tenth. And then bag of flour. There we go. And just throw things in. Okay. What do I need to do? I need to get a measuring cup, right? I need to get measuring teaspoons. What if I don't have those? Can I just use something that's, plus or minus 10 times that? Am I going to be okay? No, I'm going to have a lot of problems, right? And so one of the ways you need to think about precision and measuring stuff is that when we're measuring things, we need a certain level of accuracy. The amount of accuracy we actually know is what's called significant figures. Okay, they tell us the amount of precision that was in that measurement. So if I were to be measuring a cup of something, and all I had was a drinking cup, I could probably get, it's within half a cup or so, right? But am I going to know if I have exactly a cup or not? No, probably not, right? Same thing is if I'm measuring something and I'm trying to measure out a liter and I use one of your guys' drinking mugs, right? Am I probably going to get exactly a liter or anything that close? No, I'm going to get pretty far off, aren't I? Okay. One of the ways you can also think about this is when you're talking about calculations of money, oftentimes you just go ahead and calculate things to plus or minus $5 or so, right? Yeah. You don't usually calculate it to fractions of a penny, do you? Okay. However, when banks and credit cards are calculating things like interest, did you know they calculate it out to something like 10 digits? Okay. Do you know what they do with those extra digits? Anybody ever seen the old Superman 2? No? Okay, it's the movie that they did this. This actually was done several times. where a Ukrainian hacker group actually made a virus. They infected a bank ATM and ATM system, actually. And all that virus did is every time calculations were made by the bank, they rounded off those extra digits past the third digit. And you never know because you only see 2 digits, right? You see the tens and the single pennies, right? That's it. But they did that. All of that got deposited into a bank account, and that actually accrued, last time I checked the number, it was over $100 million that they had managed to accrue and steal. And that's because the precision that you're seeing is actually very limited compared to the precision that's actually happening in the actual measurements in the actual interest-end bank. Okay? And so that's actually an issue with significant figures, a real-world, somebody stole money issue with significant figures. Okay? Another interesting aspect of this is there was actually one of the upper people in the U.S., one of the U.S. mints, that was stealing fractions of pennies worth of copper and then selling the metal on the market. This is like 100 years ago. But yeah. So the person was making what would have been equivalent to about $10 million a year because of that. And stealing about $10 million a year from the government. Yeah, pretty wild, huh? So these are all issues with significant figures. So it's important to report calculated answers reasonably. If I have something that I've only measured very loosely, it's going to be a 1 with no decimal place, right? And that tells me I haven't really measured it that accurately. If I report a number that says something like, my measurement was 1.34265, blah, 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 that seems like I measured it super accurately, doesn't it? That seems like I really was precise. And then what if I tell you, I eyeballed it? Why am I reporting a number with 4 decimal places, right? I didn't get 4 decimal places. I know there's like 1 and some fraction. Okay. So in any measurement, the significant figures are going to be the digits known with certainty plus 1 estimated digit. So you're always going to estimate 1 more digit in any manual measurement you make. Okay, because you can estimate the spaces between the lines on like a ruler quite well. Digital devices will automatically show us the number of significant figures in the digital readout, so you don't have to estimate anything. You just read all the numbers on the readout and report all the numbers on the readout. That's it. Okay. They've actually incorporated the significant figures into the readout on the instrument. So in any measurement, all non-zero numbers are going to be considered significant. So all of the non-zero numbers that are after a measured value, so like 1.000, those zeros are significant. Okay, so let's talk a bit more about zeros. Now, zeros tend to be the part where you're going to have the most issues. These are going to be, if you're going to get tripped up, it's going to be because of zeros on these. That's because they have 2 significances in numbers. Okay? In things like decimals, those zeros are usually significant. And that's because they're there because you wanted to put them. Because you were representing that precision. You're representing significant numbers. However, when you write out numbers that are things like 1 million, do you get to choose the number of zeros you put in 1 million? No, you have to put 6 zeros to write out 1 million, right? And those are called placeholders. Okay? They're not representing necessarily precision or significant figures. They're there because you can't write 1 million without the zeros. All right? So if a 0 is a number without a decimal point is significant, it can be shown by putting a decimal point after that 0. To indicate significant zeros in large numbers, you can draw a line above the significant 0, and that says it's significant up to this 0. Then all the zeros that are after that, not significant. They're there because I needed to represent them 1 million, 1 billion, whatever. Okay? Exact numbers is going to be numbers that are used and defined conversion factors, counted items. These are going to be exact numbers with an infinite number of significant figures. These are things that by definition, they can't be fractional. I can't have 2.1 humans, can I? There's not a 0.1 human. Okay? There's 2 humans, there's 3 humans. Okay? That's an exact number because by definition, what a human is, right? I can't have fractions of humans. Okay? Okay, so this right here is a summary of those rules. This is going to be significant one right here, not a 0. For example, this right here has 2 significant figures, 41. See those 2 significant figures? We just count those, 1, 2. 41, that's 2 significant figures. This number right here, we count them up, 1, 2, 3, that's 3 significant figures. Right here, we have a 0 that's between 2 non-zero units. Those zeros between 2 non-zero units are significant. And so this number right here has 3 significant figures. This one has 4 significant figures. A 0 at the end of a number that has a decimal place, that is going to be significant. So 20 period for that decimal place, that's 2 significant figures. This one right here is 4 significant figures. See how it has the decimal place right there? Making these last 2 zeros significant. Okay, let's go ahead and look at a 0 that's not significant. It's at the beginning of a number that has a decimal place. So see this, that 0.03, that's 1 significant figure. You have to put the zeros. You won't be able to represent that number without them, can you? Okay? They're not significant zeros. They don't tell you anything about its precision. They're just there to hold the place. Okay? This one right here, see all those zeros in front? Not significant. They're placeholder zeros again. And this is 1, 2 significant figures. That's the 2, 4 at the end. This one right here, it's a large number without a decimal place. And so these last 3 zeros here, those are not significant zeros. Okay? Those are there to, again, hold the place. And so the 1 and 2 are significant. That's 2 significant figures. This is 1, 2, 3. That's 3 significant figures. Okay, folks, we'll call that a day. Please go ahead and make sure you practice problems. Okay. You all have a wonderful day. Wonderful weekend, actually.
Which about the lab thing? So the contract, it says it's due the 17th, but it says on paper, so we don't have to worry about that.
No, you just go ahead and do that whenever we start lab. Yeah, I'll have to remember to switch the date. Thank you.
I have a question. So I did the intellectual assignment and I only got like a few on it and stuff like that. How do I practice it? So does each chapter or whatever have a pre and a post?
They do.
Okay.
Yeah.
Okay.
And you should be able to do them multiple times, up to 3 times, I believe.
What do you mean?
You can actually redo assignments.
How do you do that? Oh, like completely? Mm-hmm. Oh, really? Okay, I'll look at that. Thank you.
No problem.
Do you know Mila? What's her last name? She's a chemistry major. Her name is Mila. She's on the volleyball team. She's from Portugal.
Oh, yes.
Yes, I told her I was in your class and she was very excited. She's like, I love Dr. Cole.
Yeah, she's lovely.
She's so sweet.
She is. She's wonderful.
Hi, my name is Madison. I'm the one having all the problems with Pearson right now.
Oh, okay.
So, they just emailed me actually while we were in class, and they told me that, so in order to switch my email, they have to all the subscriptions that I have, to Pearson or whatever through Cumberland.
Oh, wow.
So they're just gonna have to get a whole bunch of old information from Ball State and switch it all back. So I'm trying to get it all figured out right now, and
Okay.
I haven't done the chapter 1 pre kind of thing over.
So when you're all set up, remind me, and I can roll back any penalty.
Okay, perfect. Thank you so much.
Take care.
Sorry for all that again.
You as well. When everything's set up and working,
Yes, I finished it.
Okay.
But I was just gonna tell you that next. Okay, so wisdom teeth just started hurting. Gums are this big. I can show you if you want proof.
no, I'm good.
But anyways, I have a consultation on Wednesday to see when I can get them done. They're saying there's an available